Hey everyone, and welcome to our pre-algebra course. I'm your guide, and in this series, we're going to break down all the fundamental concepts you need to build a strong math foundation. We're starting right at the beginning with whole numbers and integers. Don't worry if math feels intimidating, we'll go step by step. Let's kick things off with something you might already be familiar with: place value and rounding. So, what is place value? It's the fundamental idea that a digit's value depends on its position or place within a number. We use a base 10 system. That's a fancy way of saying that each place is 10 times greater than the place to its immediate right. Take the number 3,456. Every digit in this number has a specific value based on its position. The 6 is in the ones place. Its value is simply 6. The 5 is in the tens place. Its value is 50. The 4 is in the hundreds place. Its value is 400. The 3 is in the thousands place. Its value is 3,000. Understanding place value is crucial because we need it for rounding.
Rounding is just a process of simplifying a number to make it easier to work with. This involves trading some precision for simplicity. You're finding a cleaner number, like a multiple of 10 or 100, that is closest to the original number. There's two simple rules to remember. You find the place value you want to round to, and then you look at the deciding digit immediately to its right. If that deciding digit is 5 or greater, you round up. If it's less than 5, you round down. Let's see this in action. For example, let's round 47 to the nearest 10. Our target place is the tens place, which has the 4. The deciding digit to its right is the 7. Is 7 5 or greater? Yes, it is. So we round up. Rounding up means we add 1 to our target digit. The 4 becomes a 5. The rest of the digits to the right become zeros. So 47 rounds up to 50. Okay, but what about rounding to the nearest 100 and the nearest 1,000? The great news is the rule doesn't change at all. When you round to the nearest 100, your target place is, you guessed it, the hundreds digit. This means the deciding digit you look at is the one immediately to its right, the tens place. Let's try an example. Round 6,281 to the nearest 100. First, find the target place, the hundreds digit. That's the 2. Next, look at the deciding digit to its right. That's the 8. Now we apply our rule. Is 8 5 or greater? Yes, it is. So we round up. Rounding up means we add 1 to our target digit. The 2 becomes a 3. Everything to the right of the target becomes a 0. So 6,281 rounds up to 6,300. And that's it. In short, understanding place value tells you which digit to look at, and rounding is the process you follow based on that digit's value.
Next up, let's master adding and subtracting whole numbers. Pay attention because these are the building blocks of almost all math operations. Let's start with addition. At its core, addition is simply combining groups to find a total. For instance, if Sarah had 6 apples and bought 3 more, you just add them up to get 9. Simple. But what about bigger numbers? If you have 123 apples and get 256 more, it's not so easy to do in your head. The best way is to do it vertically. The most important rule is to align the place values. That means the ones are stacked, the tens are stacked, and the hundreds are stacked. Now let's try an example that uses carrying. This is what we do when the sum of a column is 10 or more. Let's add 247 and 135. We always start on the far right in the ones column. 7 plus 5 is 12. But we can't fit 12 in the ones place, so we write the 2 from the ones place in our answer, and we carry over the 1 from the tens place to the top of the tens column. Now we add the tens column. Don't forget the 1 we carried. 1 plus 4 plus 3 equals 8. Finally, the hundreds column. 2 plus 1 equals 3. Now for subtraction. If addition is combining, subtraction is taking away from a group. If you begin with 769 and give away 123, you subtract them and get 646. But what happens when the top digit is smaller than the bottom? This is where we borrow. Let's subtract 151 from 423. Again, we start in the ones column. 3 minus 1 is 2. No problem there. Now the tens column. 2 minus 5. We can't take 5 away from 2. We need to borrow from our neighbor to the left, the hundreds column. We take 1 from the 4, so the 4 becomes a 3. That 1 we borrowed is 100, which is 10 tens. We add those 10 tens to the 2 we already have. So 10 plus 2 gives us 12 in the tens column. Now we can subtract. 12 minus 5 equals 7. And finally, the hundreds column. Remember, we used 1, so it's 3 minus 1, which equals 2. At its core, multiplication is just repeated addition. Think of 3 times 4. This is just a fast way of saying 3 groups of 4. That's 4 plus 4 plus 4, which totals 12. So 3 times 4 is 12. This is great for small numbers, but what about larger numbers, like 23 times 45? For that we use the long multiplication method. The method is to multiply each digit and then add the results, which we call partial products. Step 1. We multiply the top number, 23, by the ones digit of the bottom number. In this case, that's the 5. First, 5 times 3 is 15. We write the 5 and carry the 1. Next, 5 times 2 is 10, plus the 1 we carried, which is 11. This 115 is our first partial product. Step 2. Now we multiply the top number, 23, by the tens digit of the bottom number. That's the 4. Because this 4 is in the tens place, it's actually 40. To show this, we add a 0 as a placeholder in the ones place on our next line. Now we multiply. 4 times 3 is 12. Write the 2 and carry the 1. 4 times 2 is 8, plus the 1 we carried is 9. 920 is our second partial product. Finally, we add our two partial products together. 115 plus 920 gives us our final answer, 1035. Now let's talk about division. Division helps us split a total amount into equal groups. You can think of it as sharing or repeated subtraction. For example, if you have 15 cookies and want to share them equally among 3 friends, how many does each friend get? You give 1 to each friend, then another, and so on. Each friend gets 5 cookies, so 15 divided by 3 is 5. But again, what about bigger numbers? For complex problems like 145 divided by 5, we use long division. Here's how it works. We look at the first digit of 145. Can 5 go into 1? No. So we look at the first 2 digits. How many times does 5 go into 14? It goes in 2 times, because 2 times 5 is 10. We write the 2 on top above the 4. Next, we multiply. 2 times 5 is 10. We write the 10 underneath the 14. And then we subtract. 14 minus 10 is 4. We're not done. We bring down the next digit, the 5, next to the 4. Now we repeat the process. How many times does 5 go into our new number, 45? It goes in exactly 9 times. We write the 9 on the top line. We multiply. 9 times 5 is 45. We write that underneath. And we subtract. 45 minus 45 is 0. Since we have a remainder of 0 and no more numbers to bring down, we have our answer. 145 divided by 5 is 29. Multiplication and division might seem complex, but they are just step-by-step processes for handling large groups. Let's delve into factors and multiples, two concepts that are often confused but are super important for understanding how numbers work. First up, what are factors? Think of them as the building blocks or ingredients of a number. For example, let's find the factors of 12. To find its factors, we ask, what whole numbers can we multiply to get 12? Well, we can always do 1 times 12. What else? We can do 2 times 6, and we can also do 3 times 4. So the factors of 12 are all those numbers we used. 1, 2, 3, 4, 6, and 12. A key thing to remember is that factors are a finite list. They are all less than or equal to the number. Multiples, on the other hand, are the results of multiplying a number by other whole numbers. The easiest way to think about multiples is a numbers times table. Let's find the multiples of 3. We just multiply 3 by 1, 2, 3, 4, and so on. 3 times 1 is 3. 3 times 2 is 6. 3 times 3 is 9. 3 times 4 is 12. 3 times 5 is 15. And so on. As the text says, multiples go on forever. They are an infinite list. Factors are the few numbers that build a number. They are a finite list and are smaller than or equal to the number. Multiples are the many results you get from a number. They are an infinite list and are larger than or equal to the number. And that's it. Factors are few, multiples are many. Building on our lesson about factors, let's explore a very important concept called prime factorization. But before we can do that, we have to answer a key question. What is a prime number? A prime number is a whole number greater than 1 that has only 2 factors, the number 1 and itself. Take the number 7. The only whole numbers that multiply to get 7 are 1 times 7. That's it. It has only 2 factors, 1 and 7. So 7 is prime. Now look at the number 6. You can get 6 by doing 1 times 6, but you can also do 2 times 3. Because 6 has more than 2 factors, it is not prime. It's called a composite number. The first few prime numbers are 2, 3, 5, 7, 11, and they continue on. Think of them as the unbreakable building blocks of all other numbers. What is prime factorization? Prime factorization is the process of breaking down a composite number into a product of only its prime factors. You're finding the unique set of prime building blocks that make that number. The easiest and most visual way to do this is by using a factor tree. Let's find the prime factorization of 60. We start by breaking 60 into any 2 factors. It doesn't matter which ones you pick, you'll get the same answer. Let's use 6 times 10. Now we look at these min numbers. Are 6 or 10 prime? No. We just saw that 6 is composite, so we have to keep breaking them down. Let's break down the 6. What two factors make 6? 2 times 3. Are 2 and 3 prime? Yes, they are. They are on our list. When we get to a prime number, that branch is dead, so we circle it. Now we go back to our other branch, the 10. How can we break down 10? 2 times 5. Are 2 and 5 prime? Yes, they are, so we circle them. Our factor tree is now complete because every single branch ends in a circled prime number. To get the final answer, we just collect all the circled leaves from our tree. So the prime factorization of 60 is 2 times 3 times 2 times 5. We usually write them in numerical order, so that's 2 times 2 times 3 times 5. To write it even more compactly, we can use exponents. Since we have two 2's, we write that as 2 squared. So the prime factorization of 60 is 2 squared times 3 times 5. This is the unique prime fingerprint for the number 60. And that's prime factorization. It's a powerful tool for breaking any number down to its most basic parts.
Now let's expand our number world to include integers. So far, we've mostly talked about whole numbers. These are the numbers 0, 1, 2, 3, and so on. Integers include all of these whole numbers and their opposites, the negative numbers. Think of a thermometer. Temperatures above 0 are positive, and temperatures below 0 are negative. Integers help us represent quantities that have direction or show values above and below a reference point, like sea level or a bank balance. On the number line, positive integers go to the right of 0, and negative integers go to the left. Adding and subtracting integers can seem tricky at first, but with a number line, it becomes clear. The basic rules are, adding a positive number means you move to the right, and subtracting a positive number means you move to the left. For example, 3 plus 2. We start at 3, and since we're adding 2, we move 2 units to the right. Now, what about 3 minus 5? We start at 3, and since we're subtracting 5, we move 5 units to the left. But what about negative numbers? When you add a negative number, you also move to the left. So 3 plus negative 5 is the exact same problem. You start at 3 and move 5 steps left, ending at negative 2. The rules work the same if you start with a negative. Let's try negative 2 plus 3. And negative 2 minus 3? Now for the one key rule you must remember. Subtracting a negative is the same as adding a positive. Look at this. Minus negative 3. When you have two negatives right next to each other, they team up and become a positive. So 2 minus negative 3 becomes 2 plus 3. And we know how to do that. Start at 2, move 3 units to the right, and you get 5. Finally, let's tackle multiplying and dividing integers. You'll be happy to know there are simple rules for the signs. In fact, there are really only 2 rules you need to remember for both multiplication and division. That's it. If the signs of the 2 numbers are the same, your answer is always positive. If the signs are different, your answer is always negative. Let's see this in action. Let's start with the same signs rule for multiplication. First, the one you already know.
a positive times a positive. The signs are the same, both positive, so the answer is positive 12. Now the new one, a negative times a negative. Just follow the rule. The signs are the same, both negative, so the answer is positive 12. Now for the second rule, different signs. This is what happens when you have a positive times a negative. The signs are different, so the answer is negative 12. It works the other way too, a negative times a positive. Again, the signs are different, so the answer is negative 12. And the best part? These exact same rules apply to division. Let's prove it. Same signs, positive answer. See, the signs are the same, so the answer is positive 5. Now, different signs, negative answer. The signs are different, so the answer is negative 5. So when you're multiplying or dividing integers, just follow 2 steps. Same signs, positive answer. Different signs, negative answer.
We have seen about whole numbers and integers, and in the coming video, we're going to level up to fractions and decimals. We are going to take the logic you just learned and apply it to the numbers between the numbers. Make sure you hit that subscribe button and turn on notifications so you don't miss it. See you in the next one.